So in today's lesson, I'm going to be talking to you about a concept referred to as percent yield. So, we've learned some basic stoichiometry, and so we know that if given a chemical reaction equation that is balanced, and we know how much of a particular reactant is used, we should be able to, on paper, calculate how much of a product is produced. So for example, in this reaction here, I have some zinc reacting with some hydrochloric acid to produce zinc chloride and hydrogen gas, right? And so in this question, I would say, well, let's say I have 12 grams of HCl. On paper, I should be able to calculate how much hydrogen gas that should be produced. And so often, however, as we've seen in labs that we've done in class, what we expect to be able to produce doesn't actually always work out the way that we hoped. There are several sources of error that contribute to the values we expect to get to be significantly different than those that we actually get. So what comes to mind is the lab that we did where we calculated the molar mass of a gas released when the Alka-Seltzer tablet reacted. Well, many of you received answers that were far off of the expected value for the molar mass of carbon dioxide. And so there are several sources of error that can contribute to the reasons why your percent yield is not 100%. So what I want to do first is define a few important terms for you. So the first I want to talk about is the theoretical yield. So the theoretical yield is the special term we use for the amount of product as calculated on paper. So that is basically the amount that the amount of product that we expect to get using basic stoichiometry, right? So let's maybe write that in. This is using stoichiometry, stoich for short, right? So on paper, we can go ahead and we can determine how much of a product we should be able to predict. Okay, so let's go ahead and do that. Pause the video. I'm going to do this calculation, and then we're going to see what we get for the amount of hydrogen gas in this question that we should expect to get if we're reacting 12 grams of hydrogen chloride. Okay, so let's examine my solution. We'll compare it to yours, just see how you did. So the first thing that I did, of course, was I converted my grams into moles of HCl. And I found that I had 0.33 moles of HCl. And then I did a mole ratio and said, well, if I have 1 mole of H2 for every 2 moles of HCl, that means I have half the amount of hydrogen gas produced in moles, so 0.16 moles of H2. And then I quickly converted that to mass by multiplying by the molar mass of 2.02 grams per mole to give me 0.33 grams of H2. And so that's the amount of H2 that is my theoretical yield. So my theoretical yield, I'm going to write that in, right? My theoretical yield was 0.33 grams. That's on paper what I should be able to produce. Now, as we talked about already today, the amount that I actually am likely to make if I were to perform this experiment is probably going to be less than the 0.33 grams unless I have ideal circumstances. And so we describe the amount of product that you produce in a lab in real life circumstances as our actual yield. So the actual yield is the amount of product collected in an experiment using real reactants. And so often it's useful for scientists to compare our actual yield to a theoretical yield by means of something we call the percent yield. Okay, so a percent yield is a comparison of what you made in the lab to what you should have been able to make. And most people in society are very familiar with the concept of percent. And so percent yield is an easy way for us to kind of make some conclusions about how well the lab was conducted. Right, so for instance, a reaction where the yield has a very low percent yield may not be an experiment where all of the sources of error were considered properly in the design of the experiment. And you may want to revisit that when maybe trying to make improvements to the lab design in order to get a higher percent yield. And so the percent yield can be calculated by comparing the actual yield, what you got, compared to the theoretical yield, what you should have been able to get, times 100. It's sort of exactly like a test, right? What you got versus what you would have been possibly able to get, times 100. And so, we determined that we predicted the amount of my theoretical yield. Let's rewrite that, was 0.33 grams. And so from that, I should be able to figure out, if I know what my actual yield was, what the percent yield was for this reaction. So let's just say I did a reaction and I actually collected 0.16 grams of hydrogen gas. Well, then I can do a quick percent yield calculation here, right? My percent yield is going to be my actual yield of 0.16 grams. And by the way, I got that by just making up a random value. I didn't actually do this lab, but, if I had, I could have just, I'm just making that value up. It's not coming from anywhere that I calculated it. So I'm going to divide that by the theoretical yield, the amount that I should have been able to make as predicted by the amount of reactant I used, times 100. And so when I work that out, I get a percent yield of 48%. And you can sort of eyeball that by looking at those values and see it looks like it's about 50%. Right, so that is, you can decide based on your expectations for this lab experiment, considering all the limitations, and whether that's a reasonable result or not. So as we talked about, most experimental yields are less than 100%. And so what I want you to do is just take a minute, pause the video, and think about why it is that yields are usually less than 100%. Well, at the end of the day, it all comes down to loss of product, right? So that's a very general way of describing it, right? Obviously, the product you expected to make is going somewhere, but we want to be more specific about that. We want to say, well, where the heck is it going? So here are some ideas about, things that could have happened to reduce the amount of product that you're actually able to collect, right? So one that I thought about was that it sticks to glassware. I don't know if you remember the lab that we did, where we were trying to separate sand and salt through different separation techniques. And you were trying to, get that sand, that last little bit of sand out of your beaker, and it was really hard to remove. It was a bit of a pain. And so there was likely some loss of sand due to it sticking to the glassware. Some of it might go down the drain when washed. Right? So, if you're washing your reactant and it goes through, you might remember also like some of the sand in the filter paper even, because it was so fine, or, maybe when you were washing it, it went through the filter paper and it wasn't able to be collected on that filter paper. So that's one other possibility. Another one was that if it's a gas, right? So in the last experiment we did where we were collecting that carbon dioxide gas, some of that gas may have easily escaped at various points in the lab experiment and wasn't able to be measured as part of the product. Okay, and there can also be some side reactions, right? If there's some side reactions that remove some of your product from the reaction mixture, then that will affect the amount of product that you're actually able to measure. Okay, so the next thing I want to talk about is, why yields are sometimes more than 100%. And I want to be clear to say that the yield can never actually be more than, than you, like in real life, you can't actually make more product than is predicted on paper, right? That's because of the law of conservation of matter. In a chemical reaction, we're not making more matter, we're just sort of rearranging it, right? So you need to be concerned when your yield is more than 100% because somehow there's something that is adding to the mass of your product to make it larger than it should be, right? So what are some things that can do that? So pause the video and think about things that can cause a yield to be more than 100%. All right, so here are the ideas that I came up with, and certainly if you have others to share, I'd appreciate that you do that tomorrow. So sometimes other products are weighed in with the intended one and falsely increase the mass. So I'm thinking about a lab where you have a product that, like your sand, for instance, in that first lab that we did. Let me draw a little picture here. So you had your filter paper, and then you had your sand on there, and we wanted to wait for the sand to dry. But the problem is that if you didn't wait long enough for your sand to be fully dry, or maybe there were clumps of sand, that clumping of the sand indicates that there's probably some water in there. And so the water, if the sand was not fully dry, that water would have added to the mass of your sand, and you would have over-predicted the amount of sand that was actually collected. So that's one idea. And that's usually the culprit, right? So, so for example, a wet product may have water added to the mass. Another really good example of when this can happen is if you oxidize a reactant. So like for instance, if I had, I'm going to say some copper, right, metal, and I were letting it dry. Well, copper, if it's really fine and it has a high surface area, it will react with oxygen just in the air, and it will produce some kind of a copper oxide, right? And so, if it's like a copper 1 oxide or a copper 2 oxide, then, I can see right now that copper 1 oxide is going to have a higher molar mass than copper alone. So if you think what you have is copper, but it's actually copper oxide, it's going to weigh more because of the additional oxygen that's in the compound. All right, so that is the end of today's lesson. Remember that if you're trying to calculate percent yield of a reaction, you will likely have to calculate the theoretical yield of a reaction first. And then once you've done that, then you can go ahead and calculate a percent yield based on the amount of actual yield given to you in the problem. So look for a worksheet on Google Classroom. It will be attached to the same worksheet that we had yesterday for mass volume stoichiometry, but I will repost it in a separate section just so that there's no confusion about that. And be sure to save any questions that you have for me for when you get back. Thank you.